Good morning, students. In today's class, part 3 of the logarithms, we are going to discuss about logarithmic functions and their graphs and logarithmic inequalities. There is much more to discuss in today's class. It's going to be very interesting. It's very intellectual. Try to be very attentive in the class. Let's go ahead. Okay. First, before understanding what is a logarithmic function, we should understand something about exponential function. So what is this exponential function? So we generate exponential function as f of x is equal to a power x. So I already discussed this in my first lecture. So f of x equal to a power x. So now let us see how does the graph of f of x equal to a power x looks like. Okay, let us take two cases. First one, f of x is equal to 2 power x. Let us see first how the graph of this looks like. So before drawing graph, we generally take some coordinates. Okay, let's take a small table kind of thing for x value and y value. So f of x, we have taken it as 2 power x. When x is equal to 0, f of x is going to become 1. When x equal to 1, f of x is going to become 2 power 1, 2. X equal to 2, y is equal to 8, and so on. Something 6 if you put, you will be getting 64. Okay, till where we will be getting this? If you put x equal to some infinite, which is some uncountable value, we will be getting answer also as infinite. Okay, these are about the positive values. Let's talk about some negative values. X equal to -1, y is going to become half. X equal to -2, y is going to become 1 by 4. X equal to -3, y is going to become 1 by 8. See, one point we can understand here, that this function is never going to be negative. It can at most go to the value 0, but even 0 also it never touches. When you go to infinite, when you take x value as minus infinity, you will be getting the y value as almost nearer to 0. So how it is? So 2 power minus infinity means nothing but 1 by 2 power infinity. 1 by very large value is almost equal to 0. So let's try to see how the graph for f of x equal to 2 power x looks like. So when we put 0, value is 1. 1, it is 2. 2, it is 4. So it is going to increase like this. And on the left hand side, it is going to, when you go towards negative infinity, the value is going towards 0. It will never touch 0. So the graph looks like this. This is the graph of 2 power x. So when 0 it is 1, when 1 it is 2, when 2 it is 4. I think this should be very much clear how to draw the graph of f of x is equal to 2 power x. Now this graph is never going to touch the x-axis. So this x-axis, or another name for x-axis, is y is equal to 0 line. This is called horizontal asymptote. Okay friends, so this is horizontal asymptote. Similarly, okay, now about the graph f of x equal to 2 power x is very much clear. Now let's see the graph for f of x is equal to 0.5, or like just say half power x. So how it is going to vary? Let us see some values x and y. When x equal to 0, it is again 1. When x equal to 1, it is going to be 1 by 2. When x equal to 2, it is going to be 1 by 4. When x equal to 3, it is going to be 1 by 8. Can you guess what will be the value when x is infinite? Yes, it is going to become 1 by 2 power infinity. Nothing but 1 by 2 power infinity, nothing but 0. These are about positive values. Let us see something from negative values. X minus 1, it is going to become 1 by 2 power minus 1, nothing but 2. X minus 2, it is going to become 4. Minus 3, 8. If you extend till minus infinity, it is going to become infinity. So how this graph looks? y-axis, x-axis. So when you put x0, this point is going to be there 1. Now when you put x infinity, you are getting answer as y0, means the point will be somewhere here. When you put x minus infinity, you are getting y infinity, somewhere the graph starts. So here, so join these 2 points. So this is the graph of f of x is equal to half power x. Yes, students, we can see that there is a change in shape of the graph between f of x equal to half power x and f of x is equal to 2 power x. There is a change in the graph. So all the, means if at all, just to generalize this, okay, this is the graph which I wanted to say it later actually. Okay, let me have the thing here. So when you write f of x is equal to a power x, almost all the graphs looks like this. Something, somehow or other, they just passes through all this, all the graphs will pass through this point. Yes. So all the graphs of f of x equal to a power x when a is something greater than 1 looks almost of this shape. But all the graphs f of x is equal to a power x when a is 0 less than a less than 1, the graphs almost look like this. So this is the difference between f of x equal to a power x graph and f of x equal to a power x when 0 less than a less than 1 and a greater than 1. So this much should be very much clear. Fine. Now, why I am discussing about this exponential function? Okay, let's consider this function. Okay, we have taken f of x is equal to 2 power x. So on this graph, let us talk it. Okay, let f of x is equal to 2 power x, that is equal to y. The inverse of this function is going to become ln y base 2 is equal to x. So I wanted to bring the connection between exponential functions and the logarithmic functions. So now, just if at all we discuss some of the points on this graph are, ordered pairs of this graph are x equal to 0, y 1. Now next, x is equal to 1, y 2, 2, 4, 3, 8, so on. Similarly, if you take the some negative values for the x, you'll be getting something like minus 1, that's 1 by 2, minus 2, that's 1 by 4, minus 3, that's 1 by 8, minus 4, that's 1 by 16, and so on. Now if you consider the coordinate points for this one, see if you put here, um, so if you write the logarithmic function, the logarithmic function generally looks like ln x base 2, that is logarithmic function, correct? So the input should be this number. Let's give the input as x equal to 1, then f of x is going to become 0. If we give input as x equal to 2, f of x is going to become 1. Input 4, it's 2. Input 8, it's 3, and so on, right? And similarly, if you give some negative in, okay, you cannot give the negative inputs, but you can give fractional inputs. See, 1 by 2 if you give as input minus 1, 1 by 4 minus 2, 1 by 8 minus 3, 1 by 16 it's minus 4, so on. So some things we can really observe here are, see friends, when there is a 0 comma 1 point over here, there is 1 comma 0 point over here. When there is 1 comma 2 point over here, there is 2 comma 1 point over here. 2 comma 4, there is 4 comma 2. 3 comma 8, there is 8 comma 3. Minus 1 comma 2, 1 by 2 comma minus 1. So we can understand that if a comma b point belongs to 2 power x graph, then we can say that b comma a point surely belongs to ln x base 2 graph. Friends, from this what we understood exactly, that if we have 2 power x graph, exactly the mirror image of 2 power x graph in y is equal to x line. In y is equal to x line, if you take the mirror image of 2 power x graph, you will be getting the ln x base 2 graph. That's what I wanted to show in the image format. See this diagram. Yeah, so this blue color line is representing y is equal to 2 power x graph, and this red color line is representing y is equal to ln x or log x, anything is fine, ln x base 2 graph. And exactly they are mirror images for the line y is equal to x. Similarly, means if you see your face in the mirror, you will look as it is. Now similarly, the y is equal to 2 power x graph is going to see itself in the y is equal to x line as mirror, and the graph and how it looks is nothing but y is equal to ln x graph. So that's how this image shows that they are mirror images. Now let's actually draw how the graph looks like. Okay, y-axis, x-axis. Let's take the function y is equal to ln x base 2. Yeah, students, be careful. Right now, till now, I only discussed about the base greater than 1. I am taking the example of base is equal to 2, that means which is greater than 1. I did not discuss about 0 less than a less than 1, means base which is between 0 and 1. Sir, why can't we discuss below 0? That we'll see later. Okay, now when you put x is equal to 1, you are getting y is equal to 0. Let me take another ink. Yeah, when I put x is equal to 1, I am getting y is equal to 0. So this is 1 point. Next, when I put x is equal to 2, I am getting y is equal to 1. X is equal to 4, I am getting 2. X equal to 8, I am getting 3. So now, and okay, one thing we understood, that the graph is going to proceed in this way. What about the values between 0 and 1? Yes, sir, the values between 0 and 1, when you put a value which is less than 1 over here, example, let x is equal to half, which is less than 1, you will be getting ln half base 2. Value is nothing but -1, so the values are going to be negative, and the graph is going to extend like this. So here we can understand something from the graph. When x is going towards infinity, y is also going towards infinity, and when x is tending towards 0, y is tending towards minus infinity. Therefore, this line is called vertical asymptote. Asymptote is a line which actually it looks like touching, but it never touches. How much ever distance you travel, it never touches. This is called vertical asymptote. Why we are calling vertical asymptote? Before we called horizontal asymptote, now we are calling vertical asymptote. So it's nothing but its orientation. When the line is parallel to x-axis, it's called horizontal asymptote. When a line is parallel to y-axis, it is called vertical asymptote. When a line is not parallel to any of the axes, it's called oblique asymptotes. So here the y-axis, or another name we call it x equal to 0, will become the asymptote. So this is the graph for y is equal to ln x when the base is greater than 1. I think this should be very much clear. Now let's discuss the second case, that is f of x is equal to a power x when 0 less than a less than 1. I think I have already drawn the graph for that. See, the graph is already there here, f of x equal to half power x. So now, so for example, we'll take f of x is equal to half power x. Now see from here, let me change my ink to some red color, you'll understand it better. So this is going to become the graph for y is equal to something power x, where this base is something less than 1. Okay, so again it is going to become mirror image by taking y equal to x as the mirror. We can see exactly that this blue line and the red line are exactly mirror images for y is equal to x line. So now let us see how the graph of y is equal to y is equal to ln x base b, where b is 0 less than b less than 1. Okay, base is a fraction, so we have already seen the points actually. Yeah, for sure, when x is equal to 1, it is okay. Let's take for example base is equal to half. Now graph looks as it is for many, graph looks almost of same shape. When x is equal to 1, the y value is going to become 0. This is one point. When x is equal to half, yes, the y value is going to become 1. And when x is equal to 1 by 4, y value is going to become 2. So the graph proceeds like this. We can see the red line exactly matching with our graph also. So this is the graph of y is equal to ln x base b, where b is 0 less than, okay, b is a number between 0 and 1, which is a fraction. Okay, now here also we can call the y-axis nothing but x equal to 0 line as vertical asymptote. Yeah, so here finally, just to combine the whole knowledge, we have learned y is equal to ln x base b graph in two cases, that is when base greater than 1, when base between 0 and 1. So you may ask me, sir, what about the base less than 0? Logarithmic function itself is not defined. Now when the base greater than 1, what is the graph shape? The graph shape is something like this: y-axis, x-axis. What when the base is 0, between 0 and 1? This is how the graph is. So now let's discuss about domain, range, and domain, range, whether the function is increasing or decreasing. Let's discuss these three things for the two graphs. Okay, what is the domain for y equal to ln x base b when b greater than 1? You can give all the values from 0 till infinity. Here also we will discuss the domain, range, increasing or decreasing. Yeah, here what is the range? Nothing but the y values. You can understand from y values are from minus infinity to plus infinity. Every value is included, and if you see carefully, the as x is increasing, y value is also increasing, so it is going to be an increasing function. So how to say it in a mathematical terms? Okay, ln, let me write like this: if x1 greater than x2, then we can say ln x1 greater than ln x2, provided base is greater than 1. Okay, now coming to this graph, domain again 0 to infinity, range again minus infinity to plus infinity, increasing or decreasing, this is a decreasing function. Sir, we can see this actually, so the graph is going to decrease as x value is increasing. Sir, how do you say whether it is increasing or decreasing? with respect to x value. If x value is increasing and accordingly y value is decreasing, this is called decreasing function. And x value is increasing accordingly the y value is increasing, it is called an increasing function. Now here we can see in the graph that it is a decreasing function. So how to say mathematically, if x1 greater than x2, same statement, what happens here is ln x1 less than ln x2. So this is about the graphs of logarithmic functions. I think this should be very much clear. Yeah. Now let us discuss one more small thing actually here. Very simple topic, that is types of logarithms. So just now we have seen actually that bases will be there. So there are two types, that is natural logarithms, common logarithms. So natural logarithms means the logarithms for which the base is not 10, sorry, the base is number e, and common logarithms are logarithms for which the base is 10. Very simple thing. Sir, what is this number e here? So e means, why we have taken it, yeah, there is a reason for that. E has a value that is 2.71828 and so on. This is an irrational number. Like we know in mathematics we have one more irrational number, pi, which we generally use a lot of times. So irrational number. So there is other ways of expressing this. 1 plus 1 by 1 factorial, 2 by 2 factorial. Okay, there is a small mistake over here. 1 plus 2 by 2 factorial, 3 by 3 factorial, 4 by 4 factorial, so on till infinity. The other way of expressing e will be e is equal to this. You can learn in the limits chapter, limit extends to infinite 1 plus 1 by x power x. The answer is going to become e. For this you will learn in the limits chapter, no worry about that. Just remember it is nothing but 2.71828 and it's a very famous natural logarithms. In calculator you can find this under the name ln. That means the base is, by default the calculator will take the base as e. Now in common logarithm base is 10, so this is like taken for very comfortable calculations, and we can understand easily that log 1 base 10 will be 0, log 10 base 10 will be 1, log 100 base 10 will be 2. This is taken for very comfortable use. Okay, so this is about the types of logarithms. Okay students, let's see the graph for different bases. Means nothing but we are going to see the graphs of logarithms for different bases on the same graph, so that you can understand which graph is below what. So y-axis, x-axis. So now let's see first the graph of, see this is one point which is common, this is another point which is common. I think not so common, that one. No, something happened, sorry students. Y-axis, okay. Now let's imagine this is the graph of ln x base 2. Now the graph of, this is the graph of ln x base e. Okay, you'll understand why. Now this is going to be the graph of ln x base 4. See, the graph is lowering down. Very easy to understand this. See, ln 16 base 2 is 4. Similarly, ln 16 base 4 is 2. For the same x value, the graph is lowering down, and e value is 2.7128. We have seen, which is the value between 2 and 4. So these are the graphs. Now let's see the graph for This will be the graph of y is equal to ln x base 0.5. Okay, now let's take a value which is lesser than 0.5. Let's take it for 0.2. It is going to become y is equal to ln x 0.2. So as the value is decreasing, the graph is lowering more and more below the x-axis. So this is the graph of logarithmic functions for different bases on the same graph paper, so that you can compare very easily. Students, now we are going to see logarithmic inequalities, very much important. And don't get confused by seeing so many inequalities. Everything you can understand just by knowing one single graph. So first, let us have both the graphs with us, or let us discuss one graph by one graph. So I am trying to draw the graph like this. So students, can you say which graph this is for? Yeah, correct. So this is going to become log x base a, where the base is greater than 1. So and this point is going to become 1 comma 0. There will be one point here, that is mm, a comma 0. Okay, now let us see the inequalities. What we are discussing, inequalities for base greater than 1. So the first inequality what we can discuss is, okay, if a greater than 1, and in that if x greater than 1. See, x greater than 1 means all the values above x equal to 1. You can see that graph is completely above x-axis. So from this, what we can conclude, log x base a is going to become positive. This is first conclusion. Second one, if x less than 1, we can understand that the graph is below the x-axis, so we can say log x base a is less than 0. These are the two inequalities. Third one, which is very much important, I am going to draw it with the red color. See this part of the graph, this part of the graph. Now in that part we can understand that, yeah, I'm writing here in red part, the x value is between 1 and a, or we can say x is less than a, correct or not? So x value is something less than a, then what we can say is log x base a is a value which is less than 1. See, from the graph we can easily understand this. When 1 less than x less than a, log x base a is less than 1. So these are the three inequalities. Okay friends, just one more inequality is there. Yeah, from here only, when again base greater than 1 and x greater than a, what's going to happen to the graph? Log x base a is going to be greater than 1. So these are the four inequalities uh, which we can discuss when the base is greater than 1. Let's go to the base which is 0 less than a less than 1. So second case, that is 0 less than a less than 1. So how the graph is going to be? The graph is going to be something like this. So this point is 1 comma 0, and this point is going to become, yeah, this is something we can say a comma 0. So I'll just immediately mark down which is our red color graph, which is very important to discuss among the four inequalities. So this is a red color graph. First let us discuss about the remaining things. Okay, what we can say, the first inequality what we can say is, when 0 less than a less than 1, if the x value is between 0 less than x less than 1, when x is less than 1, we can see from the graph that log x base a is greater than 0. Second point, if x is greater than 1, we can see that log x base a is less than 0. Second inequality. Third inequality, which is important, I'm going to mention in the another ink. When x value is greater than a, see, we can understand greater than a means from this point, when x value is greater than a, we can say that log x base a is always less than 1. This is third inequality. Fourth inequality, when x is less than a, we can say that log x base a is greater than 1. So friends, these are the total 8 inequalities based upon the logarithms. See, if at all, just to revise, if an a greater than 1, if x greater than 1, see from the graph, log x base a greater than 0. Similarly, when x less than 1, the log x base a is less than 0. And in the red color graph, when x less than a, log x base a less than 1. When x greater than a, log x base a is greater than 1. Similarly, in the second one, the same inequalities follow. We can just derive them from the graph itself. So students, in our next class, we are going to discuss something, different types of problems, different types of problems on logarithms. So they are going to be very, very interesting. Please also see the next problem, because you'll understand what kind of models of problems can be seen in the examination patterns. Thank you very much.